So Stefan joined NewScale Technologies in 2016 in sales and precision micromechatronic products, moving to NewScale Robotics Division in 2018. He has developed partnerships with Universal Robots and Gage suppliers to develop NewScale's product offerings and also standardize automated inspection systems. He regularly works with industrial manufacturers to teach them how to use a collaborative robot with gauging instruments, helping them to automate quality tasks and improve productivity. So let me turn it over to Stefan Frederick, and we're looking forward to your talk. So take it away.
Hey, thanks for the intro, and thank you to the ASQ Rochester team for having me on and inviting me to come present. It's always nice to do local things. So again, I'm Stefan from NewScale. We're based out of Victor, New York. So I assume everyone here is from Rochester, but it's about 20 minutes southeast of Rochester. So NewScale Technologies is the parent company of NewScale Robotics. And in general, we focus on manufacturing high precision motion systems. Usually we work with industrial and medical OEM manufacturers throughout the world. Oftentimes we're moving, small optics and things like that. So originally we actually, one of the main focuses of the company was to focus the little lens that's inside of your cell phone camera. So those are the types of applications that our company has traditionally worked on. And then in 2018, we launched the NewScale Robotics division, and really have worked closely with manufacturers to help them with part handling and inspection automation applications, and really bringing together those two worlds of automation and quality control. So we're a systems integrator for the collaborative robot company, Universal Robots. So that's what most of my examples will be today as we look at some real world uses for these types of robots. And we'll jump right in here. So just to quickly, go over some learning objectives, and I'll say, I'm targeting this to be about, 30 to 40 minutes or so, and then we can jump in for questions. And certainly if you have any and want to put them in the chat, that works, or we can just talk through them at the end. So my goal for tonight is to show everyone some typical automated inspection applications and how the use of robots can be used to automate inspection processes, whether it's within the metrology lab or doing things like automating manual gauging on the production floor. I'll go through some best practices for using collaborative robots and how to apply them for high mix, small batch applications. And I have a few application examples and videos that I'll cover. Some are from NewScale and some projects that we've worked on, automating dimensional gauging, but also from some other companies and areas that NewScale doesn't typically work in, but all related to automating inspection. And some of those are things like visual inspection or automated testing. I'll run through how to cost justify and create a business case for adding automation to a quality department. And it's a little bit different than a normal cost justification you might have for buying inspection tools or metrology equipment. We'll also run through some industry trends in the manufacturing space and kind of what's driving people towards automating inspection. And again, if you have any questions, feel free to add them to the chat. So automation is now becoming more accessible to small and medium-sized manufacturers, and it's really allowing everyday employees to use these new technologies to automate repetitive processes. And it's really due to the easier interfaces that emulate some of the typical kind of app-based technologies that we're getting used to and use every day, things like smartphones, while also letting you work side by side with the robots, often without guarding or barriers between the employee and the robot. And one of the core technologies that's enabled collaborative, agile, or flexible manufacturing automation, whichever word you want to use, are collaborative robots. And these are often called cobots, which you'll probably hear a few times throughout this presentation. Some of you might already be familiar with them. And today, collaborative robots are the fastest growing industrial robot segment. Collaborative robots are different. They still do what most traditional industrial robots do. They automate repetitive and boring tasks, but this greater accessibility to automation has been made possible with cobots because of two main differences from the more traditional robotic systems you might be familiar with or may have seen in larger manufacturing sites like big automotive plants, for instance. So these cobots are categorized as collaborative because they're force and speed limited, and typically they're able to operate around people without any guarding. You got to do a safety assessment if you attach something sharp like a needle or a knife to the end of the robot arm. It's probably not collaborative and safe anymore. And then the other key difference is the interface has been made a lot more easy to use, and again takes more of that app-based approach to automation. And any new commands that you teach to the robot are done right through a tablet that controls it, called the Teach Pendant, and it's about the size of an iPad. Most of the time when people start using the robot, they can have it complete some pretty simple tasks with just about 20 minutes of hands-on time. And the fundamentals course for these robots is usually only about 2 days, and that's all most people need to learn to teach these new robots new processes. The robot interface has been designed to be usable by everyday employees, so you don't need to be an engineer or a programmer and necessarily have those people on staff to use these types of robots on a day-to-day basis. So Universal Robots, also known as UR, was a company started in 2005, and by 2020 they shipped a total of 50,000 robots. So they've taken, just kind of shows you the growth, but they've taken an app-based approach to these collaborative robots. I like to compare them to Apple for the mobile phone space, because UR asks third-party companies like NewScale to develop hardware and software to interface to their robots, and then UR will test it and certify it as a UR Plus product, and it ends up going into what they call the UR Plus App Store. So there's hundreds of different products, anything from grippers to welding kits, sanding and polishing products, deburring tools, and then quality control technologies, which is what we'll be talking about today. So I think this was a pretty smart approach that they took, because a 6-axis robot arm is frankly pretty useless without any end of arm tooling or other peripheral components that you need to actually do a task. So they've essentially outsourced this specialized type of task to third-party companies that their real core business and core objective is to solve those particular type of automation problems. So here's an example of 3 robots working side by side with a worker. This is just for a food processing application. You'll notice here though that there's no guarding around the robots, and they're working well within reach of the operator here that's right in the middle of all of them. So hard-tooled kind of traditional robots for mass production have been in use for a long time. For example, in 1961, the first Unimate robot was installed at General Motors, and obviously they've gotten a lot more advanced since then. Here I list some of the key differences between these more traditional hard-tooled automation and agile automation buckets that I'm kind of categorizing each of these types of technologies into. So a primary benefit of collaborative automation is that you can support higher mix applications, and you don't need to dedicate a robot to one task and one task only all day long. So generally it targets about 10,000 parts per month or so. So you can automate at roughly the same speed as a person, take up about the same space that a person would need to perform a task, and improve the repeatability of the process. So that space constraint is particularly of importance, if you're operating in a very small, usually space limited metrology lab, or on the production floor and have to squeeze something in next to a machine. In general, you can deploy these new automation systems with your in-house team. It takes up a lot less time to deploy the system and money to implement them. If you follow the appropriate steps and follow more of an incremental automation process, which we'll talk about as one of the best practices later in the presentation. And if you follow this sort of process of dividing up automation into smaller projects, usually you can deploy something within 3 months or less, where more traditional systems might take 12 or more. So by far the biggest challenge that we hear about on a daily or weekly basis is the labor shortage. It's frankly something we're dealing with here at NewScale in some areas as we're trying to manufacture products. And I'm sure a lot of you have experienced this, and most companies we talk to, they describe it as their top priority for the foreseeable future because they have an aging workforce, they're all retiring, and they're retiring a lot faster than new people are coming into the workforce and entering manufacturing. So really puts stress on the existing team, which is probably smaller than it needs to be. And to keep up, you got to maximize the output of each person. And if that labor is not available, you might need to look for automated solutions to fill those gaps. So, we're seeing a lot of people either consider automation for the first time or have accelerated their plans because they just either can't keep up and have these QC bottlenecks, or they just can't find enough people to produce and inspect the products they make. So, generally these larger automation systems that I've been talking about used to be too costly for small businesses to adopt, but given that collaborative automation's making solutions more affordable, I think it's interesting, some of the research that's been done by the MIT task force that I wanted to quote here. It's their task force of the work for future. And I think they show this gap pretty well between large and small manufacturers that's grown over the past 40 years or so. So they say, quoting here, in the early 1970s, the productivity measured in shipments per employee of large manufacturing establishments, which they describe as plants with over 500 workers, was only about 22% higher than in plants with fewer than 500 workers. And by 2012, revenues per employee at plants with more than 500 workers were 96% higher than those at smaller plants. Trying to explain slow productivity growth in SMEs and what appears to be their worsening relative performance seems a critical step in understanding the future prospects of U.S. manufacturing. When, why, and how manufacturing firms acquire new technology, how they find or train workers with new skills, these issues are central to figuring out why productivity lags in smaller companies. So that's the end of the quote. I think that as larger firms have invested in these new technologies, particularly in automation, that's why this gap has widened so far. And historically, there haven't been great ways for these small companies to keep up with these big companies that can just dump money into investments in capital equipment and really scale their business. So we see these as these new tools and technologies as a great way to keep up with some of the larger companies, certainly overseas manufacturing. And so far we've seen a lot of early adopters use these types of robots, but we're starting to see more and more people reach out about automation and consider it for the first time, given all of these new challenges that they're experiencing in the quality department in their company. So I kind of mentioned, quality applications have been of interest, but have generally lagged behind other more production-focused robotics applications, like machine tending, packaging, welding, or finishing type applications. So we're definitely starting to see that trend change and more people considering quality. We talked with one guy and he's like, I see everyone else getting a robot here, and I'm just in my metrology lab, and I'm wondering, where's mine? I could use one. So with some of these challenges that that I mentioned previously in mind, wanted to look here at some of the motivations that we're seeing for quality on a day-to-day basis, and the types of applications that you can look out for. So the first thing I recommend looking at is where your quality team spends the most time on manual inspection processes. So we find that robotic systems that can fill in the hours of one full-time equivalent, which, about 40 hours per week, gives people usually an acceptable return on the investment, and that can justify the use of a robot in the quality department. But if you're, at 80 hours or more, that's definitely ideal. And, obviously, if you're able to use it more, you get a faster return, and, more uptime is good. So it's definitely that 80-hour mark is definitely a good target, especially if you're running 2 shifts per day. So, if you have issues with operator to operator variations and hitting gauge R&R targets, that can also be a really good reason to automate. A robot effectively acts as a single operator. So, rather than, you might have 3 operators measuring a part on a day-to-day basis. Once you've automated, it's really just the robot doing that same task all day long. Plus, the data is being digitally recorded, and that eliminates any data entry errors that you might experience from having operators manually measuring parts on the production floor all day long. So these types of repeatability and reproducibility improvements are definitely an added benefit. We find a lot of the time, though, they don't tend to justify the purchase of an automated system. So it's, something to keep in mind, because it's, while process improvements and better yields can definitely be positive outcomes from automating in the quality department, those benefits are not as easy to predict and certainly to calculate in advance of getting the system. And they, generally don't inspire the same level of interest and motivation from the team that's approving, the system to be purchased and deployed. Immediate cost savings, and the hard ROI, immediate labor savings of that particular task. Those are really the things that we see tend to drive investment in automation, and where people find the most success with getting approval and actually deploying the system in their facility. So we'll look at some application examples. Hopefully the video is coming through pretty well, and talk about some best practices for identifying and implementing robots in Gaging applications. We find a lot of the time manufacturers don't have a really good grasp on how much time they spend on quality and inspection. I mentioned that's an important metric for identifying which types of applications you should look at for automating. And I think this is because a lot of teams, don't necessarily have one person sitting at one station doing that same thing all day long. It's a lot of different tasks. We've been talking about higher mix type applications where, you're measuring one part for a particular amount of time, and then you swap off and you're measuring something else a little bit later. So we find that, that the best candidates for automation are not the hardest QC processes you have, but they're things that are very simple and time consuming. So depending on the complexity, it might be worth automating if you spend, 4 to 5 hours per week on a particular inspection task. And if you have 8 types of parts to be inspected, each at 5 hours per week, that adds up to one full-time equivalent, that 40-hour mark that I've been talking about. Certainly if you have tasks that fill up more time, even better and easier to deploy. Depending on the application and setup for a particular project, with these types of robots, a lot of the time you might need to swap out a fixture or two, or load up a new program, but that should only take a few minutes. Again, it's kind of application specific, but being able to change from one task to the next, in about 5 minutes is, I think, pretty powerful and keeps your team flexible. So this video shows our product, the QSpan workstation. Since I'm talking from experience with a lot of these applications we'll be running through, I'll show this system a few times. We're just to kind of describe what we're doing here. We use a robotic gripper that also functions as a digital caliper. So it lets you do material handling and also part inspection, and dimensional gauging plus data logging all with one tool. So just keep that in mind as we're going throughout. If it's as it picks up the part, it is measuring it, and that's part of one of the technologies I'll talk about today. But in general, where I'm showing the basic concept that I've been talking about, automating at about the same speed as a person would need to perform at for their daily functions, take up about the same amount of space they would need to sit at a bench and inspect parts. And you get all the benefits of automating with improved repeatability, automatic data collection, and then that person can go do something that's less repetitive and more productive and better suited for a person than a robot. So when we think about ideal QC tasks to get started with, it's really the same as any automation project. I'll reiterate this because I think it's important. We find that the best candidates for automation are not the hardest possible processes that you have, and those processes that give your team the biggest headache every day, but they're things that are just simple and time consuming for your team. So approaching automation one step at a time with that in mind is important, particularly if your team's just getting started with deploying robots. And I like this quote from Joe Campbell at Universal Robots. I think it perfectly summarizes this concept of incremental automation. So if you have a 10-step manufacturing process, you don't have to automate all 10 steps to be successful. Identify one process step worthy of automation, implement it, and start generating the ROI very quickly. So this idea of incrementally breaking up the projects is really a good way to divide the big goal into smaller, more manageable projects, and also manage your expenses, reduce the risk of the project not being deployed, and reducing schedule and scope creep. It gives you a lot of smaller successes to build off of each other, builds confidence in automation after each step, and gives you, you start getting a positive return on those smaller investments as you move through, automating all 10 steps in that process in the future. So, as we look at how to get started, robots are, generally really great at doing the exact same thing over and over again. Grab parts from a known input, complete the task, move the part to a known output location, and then do it again and again. And, people are a lot better at seeing, manipulating, and overcoming unexpected challenges, unexpected part orientations or locations, adjusting part assemblies, or applying that, craftsman or technician level touch that's hard to define or quantify that only a person can do really well. I've seen, other people describe it as, when you're thinking about automating, think about if you were wearing a mitten, right? You have the only use you have is your thumb and your 4 fingers. It's like 2 points of contact. Think about if you can do that a task with, a mitten or two mittens on. And that's kind of a good way to think about, the dexterity of the robot and the type of task that could be automated. So I'll kind of break this up into, contact versus non-contact type solutions. So after you identify a gauging process or other types of inspection tasks that are time consuming and worthy of automation, it's important to identify the types of gauges you're using and where you're using them in those processes and the available automation tools to help you actually automate those tasks. So a lot of the time, the gauging is being done on the floor by the machine operators, machinists, or other production staff as part of the manufacturing process. And that's, I would say 95% of the time where we see interest in deploying these systems is not in the metrology lab, but actually on the production floor. So usually we see manual gauges being used, things like calipers, bore gauges, drop gauges, air gauges, go, no-go gauges. They're really great for checking dimensions quickly, referencing a drawing, but if you're doing them all day long, you're bound to run into some errors. It's overhead cost for your company, and you can, some people even have turnover just because they have someone doing inspection all day and it's so boring they just want to end up doing something else. Newer manual gauges have started to incorporate technology to connect them to QMS or SPC systems, embracing the trends we're seeing in Industry 4.0 of needing easy collection of digital data. And they're usually wired. There's some wireless solutions available as well. But each data point still needs to be collected manually, often by pushing a button or using something like a foot pedal. And we're seeing a huge requirement for more and more data to be collected in manufacturing processes. And that data and the integrity of the data is definitely important if you're working in regulated industry. So using robotics to help you automatically record and store that data should definitely help you improve the accuracy of the data collection. You reduce the likelihood of falsified data and help you avoid non-conforming inspection ratings. So we're starting to see many manufacturers recognize the benefits of digitalizing their data and searching for solutions to interface all their measurement tools for analysis into a single software program whenever that's possible. It's just easier to have everything in one place. So I thought it was interesting though, in Quality Magazine, they spoke to Infinity QS, and they said that after talking with 260 manufacturers, they actually found that 75% of the people they surveyed still collected data manually, whether it was these tools or something like writing it down by hand. And that 47% of those they surveyed were still using pencil and paper. And, from my own experience, that's not terribly uncommon, but it is, sort of a funny world where, we're talking about Industry 4.0 all the time, digitalizing everything, but, that's really the reality on the ground is still a lot of manual entry. So here's a contact part gauging example using the QSpan system. So use the UR robot, the robotic gripper calipers, automating material handling and contact part gauging. So the robotic caliper can measure with an accuracy of about plus or minus 5 microns, which is about plus or minus 0.2. So it's about 2 times better than most digital calipers, with a micrometer being slightly more accurate. So we use three robotic calipers because we use different fingertips to match the parts that need to handle and that they need to handle and the features they need to inspect. So here we have one gripper equipped to measure an outside diameter and others to do part handling. So, we know that gauges, we know that calipers are not the only tools that are used for automating inspection. So here we're showing the robotic caliper picking up the part from a known location at the end of a conveyor. We load it onto a bore gauge to measure the inside diameter. We bring it under a pneumatically actuated LVDT probe, which functions effectively as a height gauge, measuring the height of the part. And then finally there, we just measured the outside diameter with the robotic caliper, using precision flat fingertips to measure that OD, and then move to the next step. So usually with contact part gauging like this, we can sort of think of it as, we say, rather than pick and place, you're picking the part, measuring the part features, recording the data into your quality system, and then you're placing the part into a pass-fail location, or sorting it based on size, based on that measured data that you just collected. Some non-contact part gauging methods I have up here. They're also quite common. They have a lot of benefits. Usually non-contact systems are very fast. They have very high accuracy, and most of the time they already have digital connectivity built right into them. So it's definitely a fast-growing segment. But again, it's some of these systems are pretty expensive, and kind of fall into that sort of hard-tooled automation category that I was talking about before. They still also require you to manually load the parts in and out of the system a lot of the time, unless it's something that's inline, like measuring parts on a conveyor, for instance. And they can definitely be a bit more complex to automate, and that really depends, though, on the technology and the type of application that you're trying to use them for. So, for example, fixed laser systems like a laser micrometer that I'm showing in the middle of the screen, or tools like air gauges, those tend to be simpler to automate because there's really only one measurement being done and one variable that you have to factor into the process flow. And there's also tools for laser scanning and machine vision, but those generally will require some programming experience and can be a little more difficult for an everyday employee to automate. And a lot of the time we see that integrators or customers with automation teams tend to tackle those types of applications because they are quite a bit more complex. So I'm going to run through a few videos that are playing simultaneously. They should all come through at once. Just going to wait for this YouTube video to load. So these are some non-contact gauging applications that I wanted to highlight. Video on the left shows a camera being mounted to the end of the robot arm, and this is checking an electrical connector that's locked in position in the subassembly. And the customer had some stationary cameras they were using, which were okay, but the robot lets them get into some nooks and crannies they couldn't really get into unless they had a person do it. And the robot's much more repeatable than the person would be. The top right video, we're just loading a drill bit in and out of a laser micrometer. And I can provide these videos separately if anyone wants to see them a little bit, larger and in probably higher resolution. And then the final video on the bottom right shows how a collaborative robot can automate loading and unloading of an air gauge to do those inside diameter measurements. So air gauges, they're extremely accurate. They're reliable technology, measuring parts very quickly with micro-inch precision. And it is an older technology, and they do generally require loading with a pretty tight clearance. Here we're showing that the robot can in fact load and unload it just as a person would. So shows that you can automate some of these older types of technologies that are available. And in all three of these applications, the data from the inspection process is being recorded manually. I'm sorry, digitally and automatically, not manually. So here,
2 years ago.
mute that. Here's some hybrid applications that show some contact and non-contact techniques. So the top left video, this manufacturer was using a collaborative robot. They're picking up a part from a tray, they load it onto a bore gauge, and the bore gauge is actually seated within a laser micrometer's field of view. And that's kind of a unique application, but it lets them do the outside diameter with the laser micrometer and the inside diameter with the bore gauge all in one shot. So it's kind of two tools combined with one. And for example, if you needed to swap in a different sized bore gauge to do a different type of part, you could easily do that, and then just take the new reading from the laser micrometer, take the reading from the bore gauge. So it is still flexible, even though this application looks a little intimidating and sort of complicated, but it is, should be fairly easy to deploy and redeploy. We're also seeing some interest in some quality lab applications. I mentioned it's not the most popular and where we see the most interest, but having a lot of industries that have these big growing demands for stricter quality control requirements, more data, a lot of the times that can lead to bottlenecks in the QC lab, just because the gauges on the floor are just sometimes ill-equipped to do the types of measurements that might be needed. And we'll just throw it on the CMM, and that can end up leading to a lot of bottlenecks and really unnecessary expenses for the quality lab. And there's definitely a big opportunity cost there for dedicating your valuable inspection equipment and usually pretty valuable inspectors, your CMM programmers, to sit there and really babysit the CMM while they're just kind of loading and unloading the same part for hours on end. It's just not really a good use of somebody's time, especially if it is a CMM programmer, because they're pretty skilled technicians that can cost, anywhere from 25 to 30 an hour. So, the cost for implementing something like this would really be comparable to the annual total cost of, 1 to 2 full-time CMM programmers. This is an interesting application in a hospital. Quick warning to anyone that doesn't like the sight of blood to just look away for the next minute. This application, one robot picks up a vial for a blood sample, and then they read the barcode, and then they inspect the cap with a vision system, and they end up sorting them into one of 4 different batches for analysis. And then a second robot then picks the vial, and they end up placing it into an entry module, which carries the sample to centrifugation and analysis. So it's not really a gauging application like what I've been talking about with measuring dimensions necessarily, but I think it's a cool example of some other ways to use robots for automated inspection or automated testing. So hopefully we didn't lose anybody with that video with the blood, but I'll jump to the next slide here. I have mentioned a few times return on investment is a really important metric, and it's true for any capital purchase. So if you're looking to get started on an automation application, ROI is probably one of the first things you should understand and calculate. There's some good resources online to help with this. There's an ROI calculator from automate.org. I can send anyone a link that's interested, but there's the URL on my screen there. For any of the applications I was just showing in those videos that aren't provided by NewScale, I can't necessarily speak to the price of them, but in all of the case studies there, the customer states that the ROI they achieved was less than a year. So that kind of shows you the accessibility of some of these new types of technologies for smaller businesses. So the benefits definitely go beyond ROI here, and especially nowadays, providing world-class quality is not really just an expectation in today's global economy. It's really become a requirement as you're competing globally. So, and by far the fastest way to lose a customer is bad quality. And automation can definitely help with that. There's a lot of benefits to automated gauging that go beyond just the financials. So some include better gauge R&R, better process control, leading to better yields, and even more engaged production teams because they're doing fewer repetitive and boring jobs. And again, these are a little harder to quantify in an ROI analysis, but they're worth thinking about as you evaluate the application and weigh some of the pros and cons. This is another application example. I'll jump through it quickly. I know we only have about 15 minutes left. So in this application, the customer's just picking up the part. They're measuring several dimensions. This is a machined metal part. And really what we're doing here is just making sure the part's in tolerance right as it comes off the machine. And you know, this type of machine tool application is very common. Machining and machine tending, especially metalworking, is one of the biggest and fastest growing applications for these types of robots that I've been showing. So, you know, when you're automating these types of processes, it helps with process control. You know, you can see if your machine tool is starting to wear based on the measured value that you're getting from the part that you're inspecting. So it can help you have less of a sort of goalpost mentality of, you know, an upper and lower tolerance limit, because if you're able to just measure the part consistently, you can actually even create a closed loop system with the gauging process that lets you automatically adjust tooling offsets to compensate for tool wear and help you stay closer to your nominal dimension and just produce better parts closer to nominal every single time. So selecting the correct robotic gauge is an important step, and usually we recommend you try automating your existing gauging methods first. So for example, if you're using a manual digital caliper today, use a robotic caliper to do the same measurement. Or if you're using a bore gauge, automate that bore gauge. If you're using a laser micrometer, automate that laser micrometer. And when you do this, you're really expediting the validation and correlation studies. If we're completely changing the methodologies we use for part measurement, it definitely extends the project and development time. You know, rather than just sort of qualifying the robot and making sure it's getting repeatable measurements, you know, you have to requalify the gauge, and that's just an added step in the process. Sometimes it's required, but you know, generally, if we can avoid it, we do. Understanding that the part feature you're measuring is definitely important, and optimizing the gauge for that is important. We need to understand that we can achieve a sufficient gauge R&R, and generally the goal is less than 10%. We've had some customers that have less than 5% as their goal, but less than 10% gauge R&R is usually acceptable. So, you know, selecting the appropriate gauge is probably straightforward and understood by most of you. When you're using a robotic caliper, it's critical to understand that you have the right fingertips to make the measurement you're trying to record. So this chart is an example that follows some well-established metrology practices. For example, we'd use flat fingertips to measure something like an outside diameter, or precision sapphire probes to measure something like an inside diameter. So just like gauges, robotic caliper fingertips can be customized to a gauge. They can be customized to gauge a specific part feature. So we'll look at gauge R&R calculation to a sample part with a robotic caliper. So establishing the part tolerance T in this case is established in the drawing. So in this kind of quick example, M5 has a tolerance of plus or minus 150 microns. We interpret this as the 3 sigma value. Next, we have to determine the repeatability of the measurement using our gripper caliper, which is the gauge we're using in this case. And the repeatability is P, the gauge precision. It's a 3 sigma value. The robotic caliper has a repeatability of plus or minus 5 microns. So if we just look at this as the ratio of P over T is a percentage, capable gauge has a percentage of less than 10%. So looking at an actual set of data to flesh out gauge R&R in practice, just as an application example here, we have 10 parts, each being measured 5 times on the M5 feature. Each part has a calculated sigma and sigma squared calculated. The P is the plus or minus 3 sigma, which is 6 times the sigma value shown. And based on the T being plus or minus 150 microns, we can calculate the gauge R&R values for each part that was measured, which range up to 4.9% and show a combined gauge R&R of 3.6%, showing that the robotic caliper is capable for the part feature. If anyone has any interest in looking at some of these calculations that we've done, I do have a white paper I can share on that. This chart shows some of the typical tolerances that we've run into in manufacturing processes, and here I've highlighted the precision of our the caliper that we've been talking about, kind of overlapping this chart in the dotted green line there. Most often we find that machining is a very common application, machining and metalworking, and definitely the most demanding. Usually, honestly, the tolerances are in, especially in aerospace and medical applications, in the plus or minus 0.5 range. So very very high precision, and usually we need some other types of gauges, like what I showed earlier, like LVDT probes or bore gauges, air gauges, things like that. We get asked a lot about, how robotic systems are calibrated and maintained. Definitely an important thing to keep in mind and understand. So we use NIST traceable artifacts like gauge blocks and ring gauges to periodically zero the gauges we deploy. So this can usually be automated and performed by the robot itself, requiring no intervention from the operator, so long as the masters are stored on the workstation and can be easily accessed by the robot as part of a program. And that could really be done as frequently as you like, or as infrequently as you like. The gauges themselves are recalibrated by the manufacturers. In our case, with the robotic caliper, they can just be shipped back to NuScale for a factory recalibration, again, at whatever frequency you require. If you want to do it every 3 months, great. Every year, every 2 years, whatever it may be, based on your own internal processes. So this photo shows, one of the key components of the system that's really made these robots accessible to people. This is the UR Teach Pendant interface. You can see it in this guy's hand on the bottom left photo there. So it's a really intuitive interface. I mentioned earlier, if you use the system for, even 10 to 20 minutes, usually you can pick up on some of the basics and do something simple like picking up a part and placing it in another location. The programming and commands that you teach to the system are done sequentially. So like a basic pick and place task would be something like move to point A, then move to point B, close the gripper, capture a measurement, move to point C, open the gripper, to release and drop the part. So it just kind of goes step by step. It's really logical and pretty easy to pick up on. And once you have a program developed, it's really like using a smartphone app or loading a Microsoft Office document on your computer. You just pull open the file, hit play, and then you can leave and the robot will run itself. So if anyone has any interest at all in looking at these types of robots, there's a simulator of this interface and the robots on the Universal Robots website. It's called the UR Academy. Gives you a pretty good feel for kind of how the interface looks, how you can work with it. You can actually run through their whole simulator course in about an hour or two, probably more on the 2-hour range. But that's kind of a good way to get your feet wet, and you can do it on your own time or on your lunch or whatever. Our team's also always available, given that you guys are in Rochester. If anyone ever wanted to come see the system or have us come out and do a demo, that's always an option as well. And then, generally data transfer will happen in an ASCII format. It's usually just an Ethernet connection that plugs into your PC, and you can download the data as a CSV or an Excel file, add things like date and timestamps, serial numbers, etc. And interfaces, you can also interface directly to your SPC software or QMS. So wrap up here. Sorry, I went a little longer than I had expected, but just highlight a few takeaways. We can answer some questions. So I'll say automation now is generally a lot more accessible to smaller manufacturers than it used to be. If you haven't taken a look at them, I encourage you to give them a try. At least pop on that Universal Robots website and or Google the Universal Robots Academy and try that out. As you're actually deploying and looking for gauging applications, I think there's really two main things to keep in mind. One is tackle automation incrementally. It's really important to divide up processes into small, manageable chunks, and also try to automate your existing gauging processes first. Don't try to completely change the gauge that you're using and how you inspect the part, but see if you can just automate what you guys are doing today and use that as a starting point. So I think that's all I have. If anybody wants to ask any questions, I can stay after 7:30 if we've got some questions, but that's all I got.
All right. Thank you very much, Stefan. I was very much enthused and awestruck from a lot of the technology that you have, and I'm glad that the applications are not totally in manufacturing, but I've seen you reach out to healthcare and aeronautics, and it's good to see that this is a wide scale type of approach. Any questions from any of our attendees for Stefan?
This is Eric. I got a question for you. So I saw these people working next to the robots without any enclosures, without any safety things. I mean,
yeah.
I was with my nephew the other day, and he's playing on his virtual reality, and before you know it, he smacks me in the head. So
yeah.
If I can't trust my nephew to stand next to me, how is it that you can trust all your robots from doing that? It's very impressive.
Yeah, it's a good question. So they have force and speed controls within the robots, and there's safety settings. So you can program the maximum speed that the robot joints can move at, and you can have it actually detect forces when it collides into something. So those can be programmed and adjusted to be, because there's some application to kind of whatever level you want. There's some applications where you're doing something like sanding or polishing with the robot, where you actually need to provide a pretty consistent amount of force. But then there's other applications where whether you're handling delicate parts or just the nature of the application, you want like as little contact as possible to stop the robot. So it's kind of funny because when we're at shows or doing demos or whatever it is, I'll run the robot and I actually have the customer stand in front of the robot so that they'll get hit by it. And it's kind of a weird thing to be, beating up people that, or, presumably beating up people that might be trying to buy your system, but it shows that the robot will collide with you and it will just stop. The maximum that you should get is like maybe a small bruise or something, but you're not gonna break a limb or anything like that. And that's because of the force and speed limitations within the robot itself and the safety settings that they program into the firmware of the robot. So I kind of mentioned earlier, you do have to do a safety assessment with these things. If you're handling vials of acid or carrying around a knife, that's probably not collaborative and you need to put up guarding. There's companies that's all they do is they just do safety assessments and recommend safety features for automation systems. But usually it's kind of common sense stuff. If something's sharp, put it in an enclosure. The majority of the applications though with these types of robots are unguarded.
All right, thank you.
Yep.
I have a related question.
Mm-hmm.
How in general, how have the robots been received by the employees? Are they embracing this technology? I imagine they would be, particularly when the robot's doing the tedious, repetitive jobs. But do they see that as a threat or some sort of technology invasion?
Yeah, no, it's a good question, and probably it's one of the main obstacles that you run into if you're talking to kind of the employees on the floor. Sometimes you get sort of some weird looks from people as we're walking through with the robot, and that's the thing. You hear on the news like, oh, the robot's going to take my job, but a lot of the time, the cool thing with these robots is that you don't have to be a programmer. So it's usually those employees that are skeptics that you can put the robot in their hands and have them do things, and then they kind of become a programmer and they can run around and automate things that they find boring or repetitive. And if you look at like some of the case studies on the Universal Robots website, they've got probably 100 or something. They bring that up a lot. They have operators on the floor that are like, I really thought I was going to lose my job, within the next year, but the robot's been great. I can go do other things, and I'm actually programming it myself, which is really, really cool. So they actually end up, it kind of goes through a, sort of a normal change and acceptance model where they're kind of resistant, and then they embrace it and they start, trying to use it themselves for other things. So, it's always something to talk about. The best way to get over that is just to have everyone try to use the system themselves.
Thank you.
Yep.
Hey, Stefan. It's John Oney.
Hey.
I know we're going to be talking further on the 27th, but I'd like one quick question. Do they have a lot of like vibratory part orientating type tables with these systems too, so that the part gets orientated where it needs, where the robot can actually pick it up?
Yeah, that's a great question, because honestly, one of the biggest challenges with a lot of automation projects for quality and inspection is how do you get the parts to the system? Robots like to have known locations that they pick up parts from. So, right. If you have a single point at the end of a conveyor, that's very easy. Or you load in a tray, you can very easily program an array, so it can just run through the 100 parts that are in the tray. They do have vision-based systems that will basically teach them what the part looks like, and it can provide coordinates so that it can know the part's orientation, and where it's located in like a vibrating tray. So they have vibrating trays that are, this big, like the size of a deck of cards, and then they have
Right.
ones that are much larger than that, even bigger than like a laptop screen. So those are definitely good. We may need to, might use them in certain applications depending on where the system's being deployed and how the parts usually get to the inspectors. If they're in a bin to begin with, that might be a great use case for that type of technology to pick up those parts and do that. But yeah, the material handling portion and how you feed the parts to the system to be inspected definitely can be a challenge at times, and it's always something to think about when you're trying to automate.
Well, we've always in some cases we've actually designed like a rail system the shape of the part.
Yeah.
So when it comes off, it automatically orientates itself to fall down to a system like that. So I'm just wondering if that's what you've seen that type of thing before.
Yeah, absolutely. Well, like sometimes you almost, like, we might call them like a magazine, like you just load, you might have like 12 rails, right? And you just load those 12 rails or like chutes or ramps or whatever it is with with all those parts. And that's something like an operator can do very easily, and it doesn't take them too long to just kind of pick up parts and load them into something like that. There's definitely expenses involved when you're trying to do automated part feeding. So those types of ramps or chutes or trays, those things are a great intermittent solution. And that kind of goes back to like the incremental automation. Like maybe start with gaging, you're loading by trays, but in the future, hey, we need to have this feeding portion fully automated. Well, do the quality portion first. Once you're happy with that and, have everything settled there, then you can move to automatically feeding parts to the system as sort of the next step. So,
well,
yeah, great
presentation. Thanks.
Thanks, John. Anybody else have any other questions?
All right, Stefan, I want to thank you very much for sharing your knowledge and your understanding of robotics with our community. I think it was I just understood a whole lot, and you shared a wealth of information. Thank you for coming to this ASQ webinar that we have on a monthly basis. We should be having another in February, so if you look to your emails, I'll be making sure that you are fully aware of when that is, and it's going to be from 6:30 to 7:30, just as this was. But again, I want to thank Stefan Frederick for presenting from NewScale Robotics this that he did perform. Thank you very much. I hope everybody has a great evening, and I will see you next time.
Thanks, everybody.
Thank you.
Thank
Great
you.
presentation.
Right.
Very good. Thank you.
Have a good night.
Thanks, Franklin. Do you need research printed out, or you got that under control?
Yep, I've got probably be sending those out tomorrow.
Awesome. Hey, great job. Thanks, Franklin.
All right.
So how are you holding up with the cold?
Thanks.
Oh, but Monday was a bear.